Hello everyone, let's analyze. So today we're going to talk about subsequences. But first a theorem. If a sequence is monotone and bounded, then it is convergent. And the proof you'll do for homework. Hopefully you recognize already this result from your in-class assignment. This result will make another appearance today. So what is a subsequence? Well, a subsequence can really be thought of as just a ordered sampling of a parent sequence. More precisely, if n of k is a mapping of natural numbers to natural numbers that is strictly monotonically increasing, then a n of k is a subsequence of the sequence an. Now, what do I mean by that? What is this n of k? Well, n of k is just telling you which indices you're choosing and in what order. That's all n of k is. So, for example, the sequence of ordered prime numbers is a subsequence of the ordered natural numbers. So here we have natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, so on and so forth. That's a sequence. A subsequence is all the primes. So you see I have here in red all the prime numbers. Those are the entries that I'm sampling. You see I'm sampling the 2nd, 3rd, 5th, 7th, 11th, and 13th entries. I'm extracting them or sampling the sequence at those points to obtain the entries in those indices, which happens to be just the indices. Or another example is, given any general sequence, I could create a subsequence by sampling every even entry. So if I have a generic sequence, A1, A2, A3, A4, A5, A6, and so on, I could extract from that all those entries that are labeled in red, and I would get A2, A4, A6, A8, A10, A12. So notice what I have here. I have as my index, I have a function of k. Now notice k still counts from 1 to infinity. Right, a subsequence is itself a sequence. In other words, it's a mapping of all natural numbers to reals. This 2k just tells me how to extract from here. So for example, the third entry of the sequence, that is the number sitting in the third spot, is the number sitting in the 2 times 3, the 6th spot, which it is. That's A6. It's the 6th entry of our original sequence, but it's the 3rd entry of this sequence. So how to take this entry and map it to this entry, that is my n of k. Now note that the ordered infinite sampling of indices is strictly monotonically increasing. Right? We have to keep order. Right? It's like having an infinite line of people, and you're going to take people out of the line, but no one can skip anyone who was in front or move back behind anyone who was behind them. You have to keep the same overall ordering. So if I have an infinite sampling of indices, and remember indices are natural numbers, then this subsequence is, well, of course, necessarily unbounded. Can you explain why that is? You should be able to. Now, the sequence an converges if and only if every subsequence converges. So let's prove this. Now, as the theorem statement is an if and only if statement, we have to prove each implication. So let's prove the forward implication by supposing that an converges to some limit a. What does that mean? Well, it means for any epsilon greater than 0, there's a natural number n for which If little n is greater than or equal to big N, then the distance between AN and big A is less than epsilon. Now, let's take from this sequence an arbitrary subsequence. And the fact that this subsequence is arbitrary is important because we're trying to show something about every subsequence. Now, since n of n, in other words, if I take the big nth entry of my sampling, I have to get something from an indice that is past or equal to big N. For example, if there's an infinite number of people in line and someone is the 100th person in line, right? If I take some of the people out of line, an infinite number of people, but if I take some of the people out of line, but keep the order, the 100th person of the new line is either the 100th person in the previous line or behind that person. Right? It's impossible if I kept the ordering that the 100th person in my new line was ahead of the 100th person in the previous line. That means some people got skipped ahead, which is against the principle of building a subsequence. So n of n, that is the nth entry, the big nth entry of my subsequence, has to correspond originally to an entry past that or equal to that big N entry. And remember that n of 1 is less than n of 2, which is less than n of 3, right? Remember, these are the indices that I'm sampling from my original sequence. My index resampling is strictly monotonically increasing. So that means if k is greater than or equal to n, then n of k is greater than or equal to n of n. Right? Remember, that's just because of the strictly monotonically increasing. And n of n is greater than or equal to big N from here. So by transitivity, n of k is greater than or equal to big N, which means that this statement is true about a n of k, which is what we have here. Now, if I notice what I have in red, for any epsilon greater than 0, there exists a natural number. And if k is greater than that natural number, a n of k minus a is less than epsilon. So I've shown that the subsequence converges. Remember, my subsequence is indexed by k. Right? K goes from 1 to infinity. Right? My subsequence is a sequence, so it does have to have indices 1 through infinity. N of k just tells you where to extract those entries from my original sequence. And since it's an arbitrary subsequence, we've proven that if the original sequence converges, then every subsequence of it converges. Furthermore, we even proved that it converges to the same limit. Now let's prove the other direction. Let's suppose that every subsequence of the sequence converges. Well, the idea here is simple. One way to sample a sequence is to sample the entire thing. So if n of k is equal to k, then the subsequence a n of k is just the entire sequence, a n. And since every subsequence converges, and the original sequence is itself a subsequence, then the sequence itself converges. So that one was a little bit more straightforward. Now that we've stocked our toolbox with various analytical goodies, we can address this wonderfully strange object. Now, hopefully, you recognize the shape of this object as something similar to what you've seen before. Right? We've seen a weird thing that looked like this, but instead of 2's, there were ones. So what is that object above? Is it a number? Is it a bird? Is it a plane? Is it infinity? Or perhaps beyond? Hidden inside the ellipses lies an implicit limit. So let's represent the number that this limit might converge to by building a sequence that we would show converges to it. So we'll say a1 is the square root of 2, a2 is the square root of 2 plus the square root of 2, or the square root of 2 plus a1, so on and so forth, so that an plus 1 is the square root of 2 plus an. That's what it looks like if we plot them. It certainly does look like it converges to, well, the number 2, right? It appears that way. Not only does it appear like it converges to the number 2, it appears as if it's strictly monotonically increasing. And it certainly looks to be bounded. The first theorem we talked about today says if a sequence is bounded and monotonically increasing, it must converge. So let's use that idea as a strategy. Let's prove convergence by showing the sequence to be bounded and monotonically increasing. Now, just to be clear, that will prove only that a limit exists. In order to prove that the limit is 2, we would have to go further. One thing we could do is show that 2 must be the supremum of the set of values. But there's another strategy that we can take, and we'll see it develop here. But first, we're going to prove that a limit actually does exist. Now note that the first entry, the square root of 2, is clearly bounded above by 2. So for the sake of induction, suppose the nth entry is less than 2. All right, we know that's certainly true if n is 1. Well, if it's true for the nth entry, then I can add 2 to both sides, and I get that 2 plus an is less than 4. If I take the square root of both sides, I get the square root of 2 plus an. Well, that is, by definition, an plus 1. And that's less than the square root of 4, which is 2. Therefore, if an is less than 2, then an plus 1 is less than 2. Now, where do we know that an is less than 2? Well, again, for n equals to 1. Therefore, a2 is less than 2. And since a2 is less than 2, a3 is less than 2. And since a3 is less than 2, then a4 is less than 2. And since a4 is less than 2, then a5 is less than 2. And since a5 is less than 2, then a6 is less than 2. And since a6 is less than 2, then a7 is less than 2. I could do this all night. I could do it forever. That is, in fact, the idea behind an inductive proof. Now let's show that the first 2 entries are increasing. Since the square root of 2 is greater than 0, 2 plus the square root of 2 is greater than 2. If I take the square root of both sides, I get that the square root of 2 plus the square root of 2, which is a2, is greater than the square root of 2, which is a1. So we know that a2 is greater than a1. That's certainly true. Now suppose that an plus 1 is greater than an, right? That's definitely true if n is equal to 1. Now I can add 2 to both sides. I can take a square root of both sides. The square root of 2 plus an plus 1, that's an plus 2. And it's greater than the square root of 2 plus an, which is an plus 1. Therefore, if an plus 1 is greater than an, then an plus 2 is greater than an plus 1. Now again, we've shown directly that a2 is greater than a1. Therefore, a3 is greater than a2. Therefore, a4 is greater than a3. Therefore, a5 is greater than a4. Therefore, a6 is greater than a5. Therefore, a7 is greater than a6. And it literally goes on forever. And ever and ever and ever. That's the idea behind an inductive proof. So by induction, we have proven that the sequence is monotonically increasing. In fact, strictly monotonically increasing. And bounded above by 2. Therefore, a limit L exists. But we have not shown enough to say that the limit L is 2. Right? We've shown that 2 is an upper bound of the set of values, but we have not shown that it's the least upper bound. Had we shown that, then we could have rested our case that the strange object we were considering is in fact equal to the number 2. So let's give a quick sketch of how we're going to show that this limit, which we're guaranteed to exist, must be 2. So here's the idea. That strange object equals L. That strange object looks like the square root of 2 plus that very same strange object, which equals L, implying that L squared equals 2 plus L. And there are only two numbers that solve that equation, -1 and 2. But -1 can't be the limit, because the limit we know from our proof of the first theorem shown in this lecture, that the limit has to be a supremum. A supremum is an upper bound, and -1 is not an upper bound. In fact, -1 is less than all the entries. -1 is a lower bound. So then, if L can't be -1, it must be 2. So that's the idea. Now let's prove this result rigorously. Since L equals the limit of an, right, and we're guaranteed that L is really a number, a real number. All right, so since L is a limit, every subsequence converges to L. So L is also the limit of the subsequence a k plus 1. By the way, just to prove to you that we didn't do anything really far out here, I'm building this subsequence only by just getting rid of a1. That's all I did. I took the entire sequence and I got rid of a1. You'll notice that when k is 1, I get a2. So this begins with a2. Now, ak plus 1, by definition of the recursion, is the square root of 2 plus ak. Now, that equals the square root of the limit of that. Now, the limit of 2 plus ak is the limit of the sequence 2. Now, by the way, the limit of the sequence 2 is just 2, right? Because the sequence is 2, 2, 2, 2 forever, plus the limit of the sequence ak. Now, of course, the limit of 2 repeating forever is, well, 2. It's a constant sequence. And the limit of ak, well, we've already established that that is L. So I get the square root of 2 plus L. So how did we go from here to here? Again, that follows from the recursive definition of ak plus 1. From here to here, right, it follows from our previous assignment that if an converges to a, then the square root of an converges to the square root of a. Or put another way, if a is the limit of an, then the square root of a which is, by the way, the square root of the limit of an, is the limit of the square root of an. And since it's equal, we can go in any direction, which is how we went from here to here. 5 is a consequence of our arithmetic of convergence set of notes. Therefore, L solves L equals the square root of 2 plus L, which has solutions at -1 and 2. Thus, the limit must be 2 since -1 is not an upper bound, much less a supremum. Well, that's it for today.